Yeah, thank you for the very kind introduction. I hope I won't let you down, at least not too much. So this is my talk. This is the overview. So most of the ideas I will present today were developed in the context of transportation networks, road networks and transit networks, but they turned out to be useful for other kinds of graphs, which maybe you find more useful too. So let's start with the basics. Part one. Let's start with road networks. So this is a random part of a map. Maybe you know it. Let's zoom in a little bit more into a random part. How do we model this as a graph? So we just place nodes at crossings of streets. We put edges where the streets are, and then we put some numbers here which are just travel times. So here it's in seconds if you would take the car. Usually you store this as a directed graph, so actually consider these as two edges here where you have the arrows. If you really have direction, you only have an arrow in one direction. Okay, so many other aspects, we mentioned this, are important in practice. So you might have turn costs, so a left turn is more expensive than a right turn. Some turns are prohibited, you can't do them, there are constraints. Maybe you don't want to take a highway in a transit network, no expensive train, or you have an e-car, you need to recharge every so and so many kilometers. Dynamic updates are an important issue, traffic jams, road blockings, or things like that. So there's a if you search the literature, I mean there's also a number of large surveys, you find a huge number of algorithms. Many of them are very special purpose. You have to be careful. They work for exactly one scenario, often not the most useful one. So in this talk I just picked a few, and I will focus of course on the more general purpose ones. So a quick recap of Dijkstra's algorithm, because it's so basic and so important. So here's the graph. Let's assume we want to go from A to B, not B, D, sorry. So we start here. How does it work? You settle in order of increasing cost. This will be important for a number of things I'm going to say. So you start with this node. If you want to go here, you're already there. It's cost 0. You settle it. You relax the outgoing arcs, which means you visit all adjacent nodes. You have some tentative costs here. You can get here with cost 3, here with cost 5. You take the next one, the smallest one, which is not settled yet. 3 is smaller than 5. You relax these arcs here. Now you can get here 3 plus 1, 4, cheaper than before, and so on until you reach D with a cost of 6. And when this one gets settled, you can stop. So that's Dijkstra. I hope you have seen it before. If not, you have learned it now. So Dijkstra's algorithm is from 1956. Why even bother? It's extremely versatile. Dijkstra's algorithm, like no other algorithm, can be used for any model. Maybe you have time dependence, complex cost functions, multiple objectives. I will show you a few of these in a second. Actually, the first map services, also Google Maps when it started, OpenStreetMaps, they all used Dijkstra's algorithm or slight variations of them. And I guess many car navigation systems still do. Yeah, and it's actually not the worst idea. It's a basic ingredient in almost every advanced algorithm, usually in the pre-processing. So doing something good for Dijkstra, making it more efficient, also helps to make the pre-processing to be more efficient. And it's not fast, we will see that in a second, but it's also not that slow. It's actually, you can do it on 1 million nodes in 0.1 microseconds per second per microseconds per 1 million nodes if you really code it well. Yeah, if you make the baseline strong. I will have results in a few slides. So here's the one problem with Dijkstra's algorithm you should be aware of. Just by the way I explained it, it should be clear until the target node is settled, you settle everything that can be reached before that. Here's a picture, so I will always call the source node S, the target node T. And what I'm going to say, actually I can look here, maybe that's nicer. So here's the path. No, then I can't, then I can only point at you. This is a killer, it's actually made for aeroplanes, but I use it for, it weighs 10 kilos. So this is how the search space looks like, right? When you have settled this node, and you have to wait that long, before that you can't be sure that you have found the shortest path, you have settled everything here. Everything in that circle, that's a huge search space, right? Well, if you want one-to-many queries, if you actually want to settle everything, then it's a feature. But usually you want one-to-one queries, or very often, then it's a problem. Not exactly a bug, but a problem. So let's do bidirectional search. You just search from both sides until a node is settled in both searches. Just a node. I mean, you can't, you have to consider all the nodes in the intersection, not just the settled one. That's why I drew a little bit of intersection here. And as you can figure out from the picture, this reduces the search space by about a factor of 2, not more. So improvement, but not a big one. Also, there's a problem. Some scenarios, actually finding the target node is part of the problem. And then this is not so easy, or doesn't work at all. So I know that in your community, many of you like A-star. So let's look at A-star. What do you have? You have a heuristic function which underestimates the real distance function, so the real cost of the shortest path. And you use that to improve Dijkstra. You just add it to the distance labels. Yeah? Here's a very simple one. Let's look at that. You just use the time needed to travel a straight line distance at maximum speed. You certainly can't do it any better. Let's actually, this is actually not such a bad heuristic. Let's look at a demo for a second. So this is from Freiburg to Delft, the travel I did yesterday and will do again today in the different opposite direction. Here's Freiburg, here's Amsterdam. So as you can see, the transit routes by train, they are of course going, they are going via Paris. Yeah, interesting. But let's look at the walking path. The walking path is the pretty straight line. That makes sense, right? Because the walking path network is very dense. So in this case, A-star with a straight line heuristic would actually work pretty well. Let's look at the driving directions. They are, yeah, you see they are deviating from this. So the more it deviates from the straight line, the worse this works, yeah? So, but for road networks, there's also the speed differences, right? I mean, there are very slow roads, very fast roads, and this is an awful heuristic. So best you just forget it again. Here's a better one. It's called using landmarks. Assume you have some landmarks. I've shown one here, called it X, and you have pre-computed these paths from these landmarks to everywhere and from everywhere to these landmarks. Here's one. Now the triangle inequality tells you that this shortest path here is no bigger than the sum of this and this. Yeah, note the directions here. This is this inequality. If I just massage it a little bit, I get a lower bound here on my distance function. So I get these orange distances. Yeah, watch the directions here. I can use them as a lower bound. Yeah, so I can use them for A-star. If I have many landmarks, I can take the maximum of these. I just take the best lower bound. I can do that. And this, of course, works great if this X is very close to this shortest path here. Yeah, but since you want to work it for all queries, you need landmarks which are close to everything. You can't have that, so you will just choose a selection which is somehow dense in your network. So how does A-star using landmarks work? Well, it reduces the search space and it looks like this approximately. Yeah? So the goal direction becomes better the closer you are to the target, but so this looks much better than the huge circle, but this is still a compact set, right? If you have a big network and yeah, this is dense. All the nodes in here, you have to settle them. We will see that in a second, what that means. Actually, the second is now. So let's see, Dijkstra, A-star with landmarks. This is a classical benchmark, the road network of Western Europe. You will find a lot of this in the literature. It's 18 million nodes, 43 million edges. So this is ordinary Dijkstra, 2 seconds. So it's actually not that bad, right, for some applications. You have to scan most of the vertices. This is average query times for just average source-target combinations. Graph size pretty compact. Bidirectional saves you a factor of 2, no more. You also see it here, half the search space. A-star is 100 times faster. But you need some pre-processing, 23 minutes. So not that bad. Let's see if we can do better. So actually the road network of the whole world is like 20 times bigger. So let's go to the second part of my talk, which is road networks. So now we're talking about sophisto algorithms for road networks. So using hierarchy, that's an obvious idea. So typical road networks have roads of different speeds. So let's look at the map again. If you, let's maybe just zoom in here on this path. Yeah, you see white roads, yellow roads, orange roads. Actually, this orange is a different orange. That's because there's a traffic jam. Yeah, the white roads are the one in the city. It's actually the small ones here. These are drawn yellow on some maps, these bigger ones, and then you have the motorways. Yeah, I mean, that's just how road networks are structured, and not only road networks. So, yeah, and it's usually dense. Yeah, the motorway network, you should have one always in proximity. Otherwise, it's not a good motorway network. So by design, many shortest paths will have this property. You go from source to target, you start and end at white roads, you have some yellow roads to get to the orange roads, and then orange roads in the middle as much as possible. Actually, you can build a navigation system like this, and people have done that. There are probably still some around. So you just you use Dijkstra, and then you say, I'm 100 kilometers from the source, now don't consider white roads anymore, don't consider yellow roads anymore. Of course, it's wrong, can give you incorrect routes, but it's a heuristic. So here's a very nice algorithm. So it's surprisingly hard and took many years, decades, to turn this idea, this simple idea, into a practical algorithm. So the first attempt was kind of the obvious way to do it. You automatically compute these levels. You don't take the colors like white, yellow, and orange, but you compute them, right? And then you say at a certain distance from source and target, only use edges from a high level. The further you are away, the higher the level. So this works, but it's super involved and error prone to implement. Yeah, so people have done this and it works. You make one mistake and you get routes, but maybe they are not correct, right? So a few years later came a very nice approach, which is elegant and simple. I will explain it to you now. And this turned out to be useful for many more networks, including those, I think, which are more interesting to you than maybe road networks. So here is how it goes. It's called contraction hierarchies. So let me spend a few minutes on explaining what contraction is. So here's a subgraph, and I have a node V in the middle. It's the red one. So contraction, we are talking about removing nodes now. So let's remove this node. Here, to the right, you just have the graph with a node removed. Now, I've changed shortest paths, maybe, for the nodes that are remaining. So I can't get from U2 to W1 anymore, right? Because this was connected, this is no longer connected. So if I want to preserve shortest path, and this is what I want to do, I have to add edges again. So I could get from U2 to W1 with cost 3. So I just add this arc. Now, I could get from here, from U2 to W2 with cost 4. I could add this one, 4. Actually, I don't need it because with the newly added one, I can still get there with cost 4, right? It's not important for what I'm going to explain that the paths are the same, just that I can get there with the same costs, right? So that's the principle of contraction, contracting one node. And actually, I can add these edges. We will see that adding more edges is not a correctness problem. It's just an efficiency problem. I want to add as few edges as possible. Let's look at two examples. Here's the first example, contraction along a path. So this is the path of nodes of degree 2. You actually have that a lot in data, just by the way data is modeled. You have a road, it's not completely straight, but it's essentially just a sequence of degree 2 nodes, and just to model the geographical course you will have a lot of tiny pieces. So let's, yeah, this wiggled a bit, in case you didn't see it, here it's again and again, yeah. Let's try to contract this one. So what will we have to do? We have to introduce a shortcut, because otherwise this would be disconnected, has to be of length 7. Same here, 5, 4, we have to introduce one, size length 9. So if you want to go from left to right, you can still do it with the same cost as before. Let's contract the inner one. It's 16, 7 plus 9, 16, yeah? And now what do we have in this super simple example? Now you have the same path with only one edge instead of 4, yeah? I mean, this is not what contraction hierarchy is about. This is just a check that it does the right thing in this scenario. This has actually been a standard pre-processing in every road planner, I guess. Yeah, you take all these sequences of degree 2 nodes and contract them. Yeah, note that we could have contracted these in any order. It would have given the same result. Now here's a more interesting example. So now we have a real graph. I mean, it's a small graph, but a little bit more involved. And while you look at it, try to understand what's special about these graphs. I mean, there are some higher costs, some lower costs. So let's start by contracting. Let's contract the middle one. What do we have to do? Wiggle and wiggle again. Yeah, this one. Well, if I contract this one, I could get from here to here with cost 6. I mean, this one is more expensive, right? I can also get there with cost 11, 2, 5, 4, but 6 is better. So I would have to add a shortcut here. I would also have to add a shortcut here, because this is more cheaper than here. I have to add a shortcut here, and so on. Actually, I have to add all shortcuts of these 4 affected nodes and understand why. I mean, this is how it will look like. Yeah, I will have to add this. Why do I have to do this? Because I decided to contract a node which is on a highway, sort of, right? This is a very short cost. I'm interested in shortest path. I'm contracting. I'm starting with contracting a node on a highway. I should not do that, yeah? So contraction order matters a lot. Yeah, this is the worst contraction you can do in this network. So we don't do it. We do a different one. Let's start from here. Let's wiggle this one. Yeah. Now these two here I could have gotten here with cost 8, but anyway I can connect these two with a path of cost 4. So I can remove them without adding a shortcut. Yeah, nice. This one, do I have to add a shortcut? Yes or no? Yeah, exactly, of cost 7, right? Because this was actually cheaper. So it's okay to sometimes add a shortcut. It's part of the method. Yeah, it would be strange if you never have to add one, but it should be as few as possible. So let's wiggle this one here. This is again more expensive. I don't have to add one. 7, 3. 10, I can get here cheaper, 1, 5, 3, it's only 9, I can remove it. So actually it's a nice graph. I don't need a lot of shortcuts. Now I have an ICE, just one, just connected to one other node. I don't need to add a shortcut. Now contractions can also involve nodes and newly inserted shortcuts. In previous rounds, 7, 4 is 11. Yeah, this 7 came from a 3 and a 4, or I think so. So I also don't need a, yeah. And now I can contract the remaining ones in any order, right? This one, and I don't need another shortcut, yeah. And now so it's like a magic trick, contraction hierarchies. You put a cloth over it and then it's gone. The graph is gone. Great algorithm, yeah. Here it is again. So what have we got? We have inserted one shortcut and we have one more thing. We did this in a particular order, and this order is important. So this is the order in which we contracted it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah? So what I will do now, I will actually So with the ordering is everything. I will not talk about how to do the right ordering. Essentially what you can do, you can figure out, you can do it greedily, right? Figure out for each contraction, will this be expensive? If yes, don't do it. Do a one that's cheaper. That works quite well. So now we do one thing. We had directed arcs in both directions here. Just direct them so that arcs are only going from smaller to larger nodes. Nodes which were contracted earlier to nodes which were contracted later. So now I have a new graph. And actually, I can now drop half of the edges of my original graph. And I've just added one, right? So this is a very cool feature of contraction hierarchies. I actually get a new graph which is smaller, maybe, often, than the original one. Yeah? So actually you use less space than for the original graph. And as we will see, you still have the same shortest path properties. So now you can forget about that you did contraction. I just have a new graph now. Yeah? Same nodes. Some same costs, some new arcs, but directed now, half the number of edges. So here's a query. Let's go from here to here, source to target. Now what I do, since this is now directed edges, the search spaces now become really small. I mean, they're small anyway because it's a small graph, but maybe you can imagine that also for a bigger graph, because you're always only going upwards, the search spaces actually can show that they are kind of logarithmic in the graph size because you're only going up. Yeah? So here it's this is the search space for going from the source. And it's also super simple, right? I mean, you just do Dijkstra, but you just do Dijkstra. You don't do anything special. You do the same from the target. And the search spaces are very small. This one should also be purple, but I didn't find out how to do this in PowerPoint. So yeah, so this is actually in both search spaces. So now, just for bidirectional Dijkstra, which I explained earlier, let's look. These two are in the intersection. It's not just one, can be more. So here I could get with cost 5 and 3, here with 4 and 6. So this one is actually smaller, right? 8, smaller than 10. So now this is the correct path, and now I just have, here I actually did a sort of backward search from the target, like in bidirectional Dijkstra. I just reversed this, I have the shortest path. That's the algorithm. It's very simple and elegant and has a number of other advantages. I have a slide about this. So there's a little more magic. In this case, these are all edges from the original graphs. This path could involve some shortcuts, then you have to recover the other edges, right? And that's, but you can do that also very efficiently. So how does the search space look like? So Sabina, are you here? She doesn't reply. I think she's here. I can't see anything. So here are two pictures from Sabine Storrand, kindly provided by her. Maybe, I hope she's in the audience. So these are grid graphs of the kind used in the grid-based path planning competition, which I guess many of you know and are interested in. You can find these instances on the Moving AI webpage, and there's also more. This competition started in 2012. It didn't take place in some years. I think this year it's taking place again. So here we have some grid graphs. What you see here in different colors, don't get confused by the colors. You can tell the algorithm from the shape. This is Dijkstra, the circle. I've shown it to you before. This is a landmark heuristic from source to target, so it gets more narrow when you're close to the target. Here it's same in different colors. This is the optimal path. Let's look. And maybe you can see the red ones here. It's just nodes here and there. That's contraction hierarchies, right? Why does it look like this? Well, it's not contiguous, right? That's a big difference because there were shortcuts involved, right? Here's a red one and here's a red one, so maybe here was a shortcut, so you could just jump over millions of nodes in your search space. Actually, this is a magnification so that you can see that it's actually a grid graph. So this is like little boxes here, and then at some points you get from one box to the other box. The gray things are the edges. So this, Sabine has done this. I haven't done this. This is the path. Yeah, and the red ones are the contraction hierarchy search space, so it's really small, yeah, a huge improvement. So efficiency. Let's compare it with Dijkstra and A-star with landmarks on the same network, Western Europe. So these are the same three rows as before, and that's contraction hierarchies. So this was 100 times faster, and this is yet, well, how much faster is it? It's a factor of 200, right? So 100 times, so it's 20,000 times faster than Dijkstra, 10,000 times faster than bidirectional Dijkstra. And yeah, and look at this, it uses less space. Yeah, here it's the same as the original graph. It's much faster in pre-processing, and look at the search space, right? 280 nodes on average scanned. Yeah, you have to look at really few nodes. So in this scenario, when you have hierarchy, there's just no good reason to use A-star with any heuristic, right? It's actually not even simpler to implement. Contraction hierarchies are pretty easy to implement in the basic case. So usefulness, they are useful for a number of reasons. Here are two very important ones. Very often you want one-to-one queries. Sometimes you want one-to-many. Yeah, like in Dijkstra, or many-to-many. I mean, this is something you can't do with goal direction, naturally, right? Goal direction works when you want to go to one target. You narrow your search space towards one target. One-to-many, the nice thing about contraction hierarchies is you do some magic and you just change the graph so that ordinary Dijkstra queries are faster, right? So you can do all the good things of Dijkstra, you also have for contraction hierarchies, yeah? Alternative routes, we have seen this on Google Maps a second ago. I have a source and target. I get several suggestions. That's easy. You get that naturally, time dependent. And actually, this competition which I mentioned, the best algorithms, at least in the 14 one where I looked at the proceedings, they were all using some sort of contraction. Of course, there are many variants of this algorithm, but the basic idea is like I showed you. However, you need hierarchy, right? That was the basic idea. As I explained, if you don't have hierarchy, then this can perform poorly. And that's not the only reason why it can perform poorly. The whole third part is about this, right? And one can also be much faster, and I have a few more slides about this, not so much details, but just so that you have heard it. It's called transit node routing. So if you think that 0.1 milliseconds is slow, I do, then watch out for these two slides. So here's another intuitive observation. You are here in Delft, you want to go far away, and let's assume you are varying your target far away. And let's just do this as well on Google Maps. So prepared this here. Maybe I should take... Wow, this is a workout. It's 10 kilos at least. Maybe I should switch hands, otherwise I will get... Yeah, so, yeah, let's see. This is Delft, where we are now, the university. Let me vary the target and look at the initial part, at the Delft part of the path. Do you see that it remains more or less the same? And sometimes it snaps. So when I move this around, yeah, it's just one configuration, another one, just the initial part, right? The end part changes, of course, because I'm moving the target, but the beginning is just, there are just 3 options or something like this. And you can turn this into a super cool algorithm, and here it is. So, yeah, this is what I just showed. And I will be really, I mean, there are a number of details which I will skip. The nice thing is this can be realized super elegantly via contraction hierarchies. The first implementations were different, but basically you can do it like this. You contract your graph and you just leave the last k nodes. These are called the transit nodes. These are the highest level nodes, the most important nodes in your network, right? K is a parameter. For these nodes, you compute all pairwise distances. That's k-square distances. If k is on the order of square root of n, you can do that, you can store that, no problem. Now, you just do ordinary contraction hierarchy query, And now you just, if the search spaces meet, fine, you have an ordinary contraction hierarchies query minus the most important nodes. This will be super fast. Now it can happen that they don't meet if it's a path. This will happen for a path where source and target are further away, because then these will naturally go via a more important node. And then you can do the following. Then you have some nodes near the source, some transit nodes. You can figure out which one are these efficiently. It's 3 here and 4 here. And what you can do now, all these 3 times 4 combination of going from a red node here to one here, it's actually orange. You have pre-computed them. All these are pre-computed. So you just compute the sum of 3. Yeah, it's just 12 sums and you compute the minimum. And this is what it looks like. Yeah, that's 2.1. It didn't go up. This is microseconds, right? So this is yet almost, it's 500 times faster. No, it's not 500 times. It's only 100 times faster. But compared to Dijkstra, this is now 1,000,000 times faster, right? This is 10,000 times faster than A-star with landmarks. And now you pay a little more pre-processing. But in the way I just showed you, it's still quite simple. And you need a little more memory. So on a mobile device, maybe you don't want this, but on a server, that's of course no problem. So if you want really fast times, you should, query times, you should use this. And you don't have a search space anymore because you're not searching. You're just compiling pre-computed things. 30 minutes? Wow, my timing is just perfect because I wanted to be here. Yeah, I think this is great. I'm amazed. I didn't expect this. I expected to. Okay, so transit networks. So I have 20 minutes for transit networks. So what's different in transit networks? Public transit going by bus. Here's an example from a conference in Dallas. Here was the hotel. There was a museum. This was not related to the conference. And here we have, yeah, it's a typical transit query. You're leaving at some time. Market Center Station, taking the green line, that's how it's called. You leave at Victory, you do a little walking. Of course, transit is highly time dependent. Yeah? And we see 3 ways how to model this on the next slide. Time dependence can be relevant for networks too, right? If you have traffic jams at certain times, it takes longer to go a certain road and so on. But here, of course, it's the main feature. So here's one way how to model this. It's called the time expanded model. You just, every event where some vehicle arrives or departs, you put a node, right? So here you have some bus leaving Market Station at 1947, right? Takes 3 minutes and then you are at Victory Station at 1950. Or you just wait till the next event here at 20:02, 15 minutes, and then, and so on, right? So that's one way to model it. It's called time expanded model. This is more complex in practice. You also have nodes for transfers, which are not free, but then it just becomes a little bit more complex, but the same picture. This is the time-dependent model, which is also useful for road networks. So you just have nodes here. Here it's 1 per line. You could also have just 1 per station. And now you have, if you go at 1947, it takes 3 minutes. If you go at 22 with 3 minutes, here it always takes the same time because it's, yeah, the lines are going in parallel, but these could be different times. You just write the schedule there. Or if it's a road network, you write the typical times according to traffic at the different times of day. You can put a function there in a road network, right? We will come back to this in a second. You can also model frequency. It looks like this. This is important for transit because by design things have a high have a lot of periodicity. So there's from, yeah, let's say 7 to 10 every 30 minutes, 3 minutes. It's just more compact. I will come back to that in a second. So what are the challenges? Now this is very strongly time dependent. You can have this for road networks too. Most navigation devices don't really do it, just in a very trivial way, but to a much lesser extent. For transit networks it's inherent, right? The travel time, that's a huge difference. Let me explain very briefly what's the problem. You don't have this in road networks. If you go to the next village, maybe the regular time is just 20 minutes, but now it's the evening, you have just missed the last bus and you are asking your system and it will tell you it takes 12 hours. Why? Because you have to wait until the next morning, first bus next morning. So the connection is 12 hours. Think about Dijkstra. In 12 hours, you have the whole transit network of the world. You can go to the airport in the evening and take a plane and go to the US, and then you can take the subway there. And then Dijkstra will explore this whole search space, before you get to your village next time in the morning. So that's a big problem. You don't have that in road networks. You have some variation in speed along path, but not that much. That's the major problem. Multi-criteria is important. Typically, one very standard thing is time and transfers. Maybe you can go without switching vehicle in 4 hours or a little bit faster with one vehicle switch, one transfer. You want both, right? Because here this one is minimized, here this one is minimized. So you will compute a Pareto set. And there's almost no hierarchy on the city level. Let's look at the transit maps of one city actually. This is the city of Stuttgart. This is just subway lines. I mean, there's no hierarchy here, right? If you think about how our subway network structured, it's just that you can get from everywhere to everywhere, but there's no main subway line, right? There's no highway subway line. It just doesn't work like this. The same for buses. You have a huge city, you want to get from everywhere to everywhere. And there are other maps here too. Also for bigger areas, it's no different. It just depends where you want to go. You will take the corresponding line. Actually, this is a different line of works. We have drawn these, which you just saw, fully automatically from schedule data. It's also a cool line of work, but totally unrelated to what I'm telling you here. So Dijkstra's algorithm can handle all this. I told you it's very versatile. It can handle everything. The algorithms from part 2 cannot, so you can't use contraction hierarchies for this, right? Already for this reason, but it also has problems with, it can deal with time dependency a little bit, but not much. And multi-criteria is also hard. This is just to remind you, in case you forgot it, that was Dijkstra's algorithm. We will look at it again. I told you it's very versatile. Let's just look at this in a little more detail now. So this is how it went. This is now one relax operation, right? Relaxing, this is one step of Dijkstra's algorithm, right? You have done Dijkstra for a while already, a few iterations. This is one edge, 3 minutes. You already know that you can get here in 35 minutes from your source node. So now something new happened. You found out that you can get here in 25 minutes. So relaxing this edge, 25 plus 3 is 28. Now you can get here faster, right? That's standard Dijkstra. So in the time expanded model for transit, you can just use standard Dijkstra, but you get a huge graph. How does Dijkstra work in the time dependent model, which you can also use for road networks? Now you have a complex function or schedule here at this edge, right? And now the situation at a certain time, intermediate time in the Dijkstra computation, you have a set of labels here, right? At this time I can get here in 50 minutes, at this time in 50 minutes, at this time in 30 minutes, right? And now, so you have a set of labels, not just one. Now new information comes in, which is also a set of labels. We don't have time to do all the details here. You have sets of labels here, sets of labels here. Now you have put these and these together. That's also, it can be done. This is what comes out. And now you have to merge these. And I will not do it in detail now. This is now no longer optimal. This is not optimal, and you just have to merge label sets. This is what you have to do, but you can do it, right? So multi-label Dijkstra, this is how it works. And this is also no longer optimal, because it's dominated by a solution here. Yeah, the new label set contains a mix of old and new labels. Also in this frequency-based model, which is very important for transit, yeah, it gets more complicated, but this is to show you how versatile Dijkstra is. Yeah, you can do anything basically along the edges and at the nodes, and it still works. The basic principle still works. So now I'm coming in here with a time range, a periodicity, and a time, and I can have multiple of those. Now there are different periodicities, so I have to find a common periodicity here, and I have to figure that out. We are not going into the details, just to show you the principle that you can also do this, right? And now you have to merge those with the previous labels, and it gets really messy, but you can do it, and it actually pays off if you have a lot of periodicity, right? So here's one algorithm which I want to show you for transit, and it's the last one which I will show you. It's the algorithm which is behind transit routing on Google Maps. So I was at Google for 1 year in 2008, 2009, a little longer than a year, since 2010. This is in production. This is a fully realistic model. I showed you on a slide what's all important in transit networks and a few more things. It's fast. I will have a slide on this, and it's also simple and elegant. I will explain it to you on the next slide. So here's the basic idea. So that's the last algorithm. I hope you are still with me. I can explain it, the basic idea, on one slide, and it's a nice idea. So remember, the problem with transit networks is the strong time dependence. That's really the biggest problem. So we have to deal with time somehow. So here's my standard example for transfer plan. Let's assume not Freiburg-Delft, but Freiburg-Zurich. I now look at all connection at all times of the year, at all days of the year, at all times of the day. How can I get from Freiburg to Zurich in Switzerland? And it turns out there are just two patterns when I go with public transport, also including bus and tram and everything. Either I will take a direct train, or I will switch in Basel. Yeah? I will take a vehicle to Basel and from Basel to Zurich. That's it. This is all the connections. I can summarize them like this. So this is like a summary of all shortest paths from Freiburg to Zurich with time factored out. That's the main idea. So whenever you have time in your model or in your problem, consider this idea. Yeah? At query time, I will now So I actually want to go from Freiburg to Zurich at a particular time. I will fetch this graph from what I have pre-computed. And now let's assume I'm here at 10 in the morning. And now I just check the schedule, the local schedule of Freiburg. 10 in the morning, when is the next train to Zurich? I can be at Zurich at this time. When is the next train or bus to Basel? Okay, I can be at this time in Basel. What's the next there? When can I be at Zurich? I compare the two, I get the best one. I will show to you in a second how this query graph looks like in a more realistic scenario. Yeah? And that's a simple problem, right? What I have to do at query time. It's just lookups of these direct connections. There are not so many direct connections. So this is, you can consider this as an extremely compact representation of all optimal paths, right? And time is factored out. I already said that. That's the main idea. So when you want to build a system out of this, which we have, you have the following components. First, you have to compute, basically pre-compute all shortest path, right? All pairs shortest path. That sounds hard. It is. I will come back to this in a second. Then for these direct connection lookups, right? Next direct connection to Zurich, give it to me. That's easy. That's just like the schedule you have at a train station. You can do it super fast. Now I have a query. I want to go from Freiburg to Delft. Give me the construct. What are all the patterns? And then actually try out all the patterns. And I have a slide on this. This is how it looks like. So let's assume this is Freiburg to Delft, where I'm now, where I live. Yeah, it's A to B, as it should be. And this is now the query graph. So this is over the whole year, over all times of the day, all possible ways. this works. Maybe I have to go to this station, so this is walking, it's switching stations, or it could also be driving, but here it's walking, yeah? And this is actually taking a vehicle without switching vehicle from station J to L. So maybe I can go to this station, take a train here, walk to this switch here, then take a bus here, go here, and this, yeah? So it's again a graph, and I can do Dijkstra again on that graph. And what does the Dijkstra do? Well, if it's at a so ordinary time-dependent Dijkstra, I showed you how it works. Walking arcs, well, they have a fixed time. They are easy to evaluate. And this is now, this doesn't have a number written on it, but I have to look up, right? Okay, I'm now here at a certain time. How do I get to this station? Yeah, what's the next best way? I just look it up in my data structure. But it's also quick, and you can do it with Dijkstra, right? And the query time, so again, you're reducing the problem at query time to a much smaller graph, right? It's a few milliseconds per 1,000 arcs. Now, I told you there's one snag here, and that's you have to compute all transfer patterns conceptually between all station pairs, right? Now that's quadratic. We all learned that at some point that quadratic is not good, or maybe it is. Actually, it's quadratic in the number of stations, not in the number of nodes when you have this time expand, not in the number of events. It's not so totally bad. Even for the transit network of Germany, which is huge with 250,000 stations, this is just 62 gigs, right? So if you store just a few bytes for each pair, which works, then this is still feasible. For larger networks, now this is just very high level, just the main idea. Yeah, you can do something like this. You can automatically, of course, cluster your network. And now in your clusters, you do these all pairs things, which you can do even for pretty big clusters. You can do it with much bigger clusters here. But, and this exploits the fact, I told you earlier, on the city level, even on the level of a metropolitan area like New York, you don't have hierarchy, right? So all these hierarchical approaches don't work. But of course, if you go from one big city to another, you have some hierarchy, right? You won't go from the east coast of US to the west coast using only a local connection, local trams or something. You will use an overland bus or a train, long distance train or something, right? So this can be exploited by this method, right? And so you want a clustering so that you have a few border stations here, and yeah, I'm not telling you about the details here, just that something like this exists. So let's look at the efficiency of this one. There are many scenarios on which you can evaluate this. I take a very simple one. You have two criteria, travel time and number of transfers. You want to optimize both, which means you have a Pareto set. That's what most transit planners do, right? You get a slower connection if it has fewer transfers. That's what some people prefer. They want to transfer less. They are willing to travel a little longer for that, right? And let's compare that with a, yeah, Dijkstra is not so bad, and I think most of the planners out there are using some variant of Dijkstra's algorithm. And you will see it's not so bad. If it's maximally cache efficient, no priority queue, two data sets here. So this is, yeah, it's not really Dijkstra anymore. The nice thing, I'm not sure whether I mentioned this. If you are, I think it was on the slide, in the time expanded graph, when the nodes are events, you have an acyclic graph, right? You can't go backwards in time. And in an acyclic graph for Dijkstra, you don't need a priority queue, right? You can just go in time order or in order of the topological sort. You can drop the priority queue, that makes your Dijkstra much faster. And then you can pay attention so that you basically just scan all the nodes in the order in which they are stored in memory, so they're super cache efficient. And then you can do something like London in 50 milliseconds, which is good enough, yeah, even for a map service. But understand, look at the first two lines here. I mean, what you're doing then, even if you're just going a relatively short distance, you will always scan most of the networks. Huh? You're just arranging your data, and basically for every query you will scan over everything, and you're just doing it super fast. That's not so bad. So for London, where the graph has 5 million edges in the time expanded model, 50 milliseconds. If you go to Germany, which is like almost 20 times larger, it will be 18 times. Yeah? So the problem with this approach is it doesn't scale, and there's no way you can make it scale, right? So if data is only large enough, it won't work, which means you can't use it for a map service. And you don't want to tell your user, sorry, your source and target were too far apart. Goodbye. You don't want to do that. So transfer patterns can do it. This scales. I've only shown it for Germany here, but it also works for, the query time doesn't change that much. Only this changes. That's of course, 541 hours it's feasible, right? It's a hard problem. With the clustering, you can actually improve this. You pay a little more in query time. Yeah, and it's actually work in progress right now to get this to work on larger graphs. Yeah, and these results are extrapolated. Okay, this is already my last slide. Hope you are happy with that. So let me just very quickly, the main messages maybe. So Dijkstra's algorithm, it's old, but it's not that bad. It's extremely versatile, and it's a key ingredient. Yeah, every algorithm I explained to you used it somewhere. When there is hierarchy, go for contraction hierarchies. It's the best method, or something involving contraction is just a great technique. If you want ultra-fast query times, you can do it. Yeah, microseconds. You have to invest in the pre-processing, but it's often worth it. When the models become more complex, or you have little hierarchy, like in transit, then the routing problem becomes much harder. Then you can't use contraction hierarchies. You have to do something different. And fast running times can still be achieved, but you have pre-processing is now more extensive, and I skipped over most of the details. The algorithms become pretty complicated. So actually, if you're interested in this problem, I mean, this is where still a lot of work can be done, right? This is certainly not, the basic idea is simple, but where we are right now, a lot of pre-processing and very involved algorithms. So that would be great to also get that to a much simpler level and also faster. Okay, that's it. So thank you for attention, and I hope that you learned something. I'm happy to get some questions. 1,000 people.
I can't throw that far, sorry. We need some routing for the throwing. I can't throw that.
You need a routing service?
All right. All right, thank you.
Where are you?
I'm here, sorry.
Yeah.
You see me?
It doesn't matter. I don't see you, but yeah.
Okay. Many optimization algorithms just need a distance matrix as input, and then there's this whole complex algorithm which comes after. So getting the distance matrix is, well, as you've shown, already very hard. If you want an all-pair shortest path distance matrix, Floyd-Warshall runs in cubic time. How would you do it? How would you solve it efficiently?
So is your question how to use these techniques to solve the all pairs shortest path problem?
Yes, so most of your talk was about one-to-one queries, like how to get from A to B. But if you want an all-pair shortest path, you need to run a whole lot of these queries, or you need to do something else.
Yeah, I mean, yeah, let me think. So I had this one slide where I said that contraction hierarchies also works for one-to-many and many-to-many queries. So, I mean, that would be my first guess. Let's assume you have a network with a hierarchy, and now you just do contraction hierarchies. And now you just do the contraction hierarchy query algorithm. And the question is whether it will be faster than in the original graph. And I think it will be, right? Because what contraction hierarchies do is you just massage the original graph so that subsequent Dijkstra queries are faster. So I think if you have hierarchy in your network, that's a better way to compute all pairs shortest path. I mean, let me just, does anybody disagree in the audience? Yeah? No. You don't have a microphone, so you can't disagree. Nobody disagrees, great. So it's this one, right? This is what many-to-many routing. I mean, since it's not goal-directed and you are just making the graph more restricted without... Yeah, I think it's...
Okay.
Yeah?
Yeah. You want them?
Thank you for a great talk.
Thank you.
What happens when you have non-planar graphs and more complex graph structures? What do you anticipate these techniques will do, and where do you think the problems might be?
So the question is, what if we don't have non-planar graphs? It doesn't matter for anything that I explained. Planarity is absolutely not important. I mean, for all the algorithms in part 2, just hierarchy was important. You can have, I mean, the graphs which I showed happen to be quite planar. Road networks are not perfectly planar. You can have bridges and tunnels. Planarity is not important. Just hierarchy is important. The fact that shortest path tend to use certain edges more often. As long as you have that property, it will work. And for the transit, planarity is also not important. It was not an issue at all. So it depends on other properties of the graph.
Thank you for your talk. I have a question regarding, let's say, the city of Delft decides to build news stations. How are you going to update this with your pre-processing and so on? Because this might be really expensive if you just add 2 stations and you recompute everything.
Yeah, that's a very good question. So the question was if I have to redo the computation, and I should find a better way to... So actually here it's no problem, right? 5 minutes, contraction hierarchies, you can just do it. I mean, unless they build their new stations really fast. You can also, even for updates to the... Actually, there are special algorithms which I didn't talk about, which have a 2-stage process. So they are called customized and so on, some other name. And then you can even do the refitting to a new metric in a second or so. But I mean, 5 minutes you can always do that. With transfer patterns it's a little bit different. I guess maybe you are relating to that number, to the 541 hours. Actually, I think, at least when I left, this is still how it was done. You just do this every twice a day or so. I mean, you can easily parallelize this. I forgot to mention this. So if you parallelize it on 1,000 machines, it's less than 1 hour, and you can still do it the same way. But these transfer patterns have a nice property. They are robust against the changes, right? If you build new stations, it's a problem, but if something gets cancelled here, then you will still find the other path. So they have a certain robustness. We have also done work about this. I've not shown it to you here. Delays and cancellations actually don't matter. You will still find the optimal path, or you just recompute from scratch. It's a very good question.
So So thank you. We need to finish the session because the technical session starts already. So thanks, Hannah, again. I'm sure she will take questions in
Yeah,
the break.
thank you very much. Thank you.